So right now we're going to talk about permutations. A permutation is an arrangement or an ordering. The number of arrangements of n items taken r at a time is given by the formula n factorial over n minus r factorial. That's right, that exclamation point symbol is a factorial symbol. For example, 3 factorial is equal to 3 times 2 times 1, which is 6. 8 factorial is 8 times 7 times 6 times 5, all the way down to 1, which is 40,320. By the way, 0 factorial equals 1 by definition. So, for example, if we had 5 people waiting to be seated at a movie theater and there are 3 seats left, we could list out all the possibilities for persons A, B, C, D, and E. And remember, order matters here, arrangement matters. There would be 60 ways. Now that's the long way to do it, and you really don't want to do it that way. Let's use the formula. We write 5p3, and your calculator has a permutation key under Math. If you go Math PRB, then you'll see the permutation key, and then you'll be able to enter the formula. So 5p3 is 5 factorial over 5 minus 3 factorial, according to the formula, and that equals 5 factorial over 2 factorial, which comes out to be 60. So that's the quick way to do this problem instead of listing them all out. So let's work a few examples. How many 5-card arrangements are there of hearts? In a deck of cards, there are 13 hearts. If we want 5 of them at a time and we're concerned about arrangements, we do 13p5. We can work that out by hand, or we can plug it into our calculator to get 154,440. We'll work another problem right here, number 11. How many ways are there to choose a council of 3 people from a group of 10, in which one person is president, one is vice president, and one is treasurer? In other words, they all have a different role. So really, ordering or arrangement does matter when we choose those 3 people. So because of that, we use permutations. Always use permutations when order matters. We say 10p3. If we plug that into our calculator, we will get 720 different groups of 3. Let's work one more, number 14. This is a variation on this idea. It's a permutation problem, but we're really not going to use the exact permutation formula. In this case, we have 8 identical science books, 5 identical history books, and 4 identical math books. How many arrangements are there of these books on a shelf? The problem is, if I make an arrangement of these books, all of them, and I move one science book over for another, remember they're identical. So that really doesn't make a new arrangement just because I swap science books. Or maybe if I swap one history book for another. Remember, all 17 of those books are on a shelf. So the way we do this is we put the total number of books factorial on top. That would be 17 factorial. And then on the bottom, we divide out all the duplicates that we would get from swapping a science for a science, or a history for a history, or a math for a math. So we put 8 factorial times 5 factorial times 4 factorial on the bottom. So work the rest of these problems, and we'll go over them in class.